Honda's TPI system. That's what this program's about. Now, in this program, we assume you already know quite a bit about how TPI works. Either just because you're a natural-born expert on the subject, or because you've studied the preceding program called Transistorized Pointless Ignition, how it works. That film strip gives a solid foundation of knowledge that's essential for working on TPI, so don't miss it. Our objectives for this program can be simply stated. First, we want to show you how to check and adjust the ignition timing on TPI-equipped motorcycles. It's a simple procedure. We just want to make sure you understand it fully. Second, we want to show you the correct procedure for troubleshooting and fixing a no-spark problem on TPI-equipped motorcycles. And we've got a special job aid to help you with this. So let's get started. We'll begin with ignition timing procedures. You'll recall from our previous program that only the CBX requires a periodic timing inspection, and there just to account for the possibility of gradual wear in the primary chain, which drives the pulsar generator. In the CBX, the timing may shift a few degrees as the chain wears and stretches, so that's why it must be checked periodically. On all other TPI-equipped motorcycles, the pulsar generator is mounted directly on the crankshaft, and under most normal conditions, the timing won't change. No periodic inspection is called for. Here, you need to check the timing only when there's a specific problem that needs troubleshooting. Now, here's a list of some of the problems that can be caused by incorrect timing: hard starting, loss of power, misfire, knocking or pinging, backfiring, and overheating. Of course, just like with other types of ignition systems, any of these customer complaints should cause you to check the timing adjustment. Now, one of the nice things about TPI is that on most bikes, you can do a visual check of static timing. And the static timing procedure is just as accurate as a dynamic check with a strobe light. If you've got a good, healthy spark from the TPI system, but the bike won't start, being able to perform a static timing check is especially helpful. It's just 3 easy steps. First, position the number 1 piston near TDC on the compression stroke. Second, align the timing mark on the rotor with the timing index mark on the case. On this Cb750, the FS stands for firing static. The FI mark stands for firing idle, and it's used for dynamic timing with a strobe light. And third, check the alignment of the rotor tooth with the tooth on the coil for the number 1 cylinder. This alignment must be exact, spot on. A misalignment like you see here is not acceptable. Even half the width of a tooth is too much error, and an adjustment is needed. To adjust the timing, loosen the screws that hold the base plate to the engine case. And turn the base plate so that the teeth on the rotor and pulsar coil are precisely aligned. Retighten the screws, recheck the tooth alignment, and that's it. Adjusting the alignment of one pulsar coil takes care of any others at the same time, because the coils are factory adjusted to the base plate. Static timing on the CBX is about as easy as on any other motorcycle. Here, you'll align the F mark on the crankshaft with the index line. There is no FS mark on the CBX, just an F mark. And then on the primary shaft, you'll check to make sure that the rotor and coil teeth are aligned for the number 1 and 6 cylinders. Same procedure. All right, next let's look at dynamic timing procedures. Using a strobe, you can check both initial timing and advanced timing. However, you do have to use the right F mark. For initial timing, it's the FI mark for fire at idle that you've got to align with the index. To check timing on 4-cylinder machines, connect a strobe light to the number 1 or number 4 cylinder. Start the engine, and aim your light at the index mark. With the engine running at the specified idle speed, 1,000 RPM for this Cb750K, the FI mark should align with the index. To check the advance, gradually rev the engine to the maximum advance speed specified in the manual, 7,400 RPM for the On the 750, these marks are kind of small because they fall right next to the pivot point for the centrifugal weight. If the initial timing is okay, but the advance marks don't align with the index at the specified speed, well, that means you've got a problem with the advance mechanism. Remove the rotor and check the mechanism. Check for smooth operation, proper spring tension, and a full range of travel. Sometimes a little light lubricant will cure a sticking mechanism, but otherwise, replace the whole unit. To check the dynamic timing and advance on the CBX, you will temporarily install this degree wheel over the rotor. It's a special tool available from Honda. Then, with your strobe, you'll check advance at both 2,500 RPM and 8,000 RPM. The Honda shop manual gives the full procedure. Checking dynamic timing on a TPI-equipped GL 1100 is about the same as before. You'll install the timing inspection cap in the case and connect your strobe to plug number 2. Start the engine, and at idle speed, check that the F mark aligns with the index mark on the case. To check the vacuum advancer, begin by removing the cover for the pulsar generator. Connect a Mighty-Vac directly to the vacuum advancer, like you see here. Now the goal is to see that the advancer does operate as vacuum is applied. The advance should begin with a vacuum of about 4 centimeters of mercury, and full advance should be reached by 10 centimeters of mercury. If the advance doesn't work properly, it should be replaced. All right, that pretty well wraps up most of what you need to know about spark timing with TPI ignition systems. Really, the procedures are quite conventional and straightforward. So let's move on to the second part of our program, troubleshooting procedures for the TPI system. Now, some guys might want you to think that their troubleshooting ability involves a little black magic, but don't you believe it. A big dose of common sense is what's needed. Let me show you what I mean. Joe here is a Honda registered technician, and he's just starting to work on the Cb750. The customer says it won't start. He had to haul it in. And Joe's mind immediately begins questioning.
I wonder what it is. Gas, compression, spark? Something's missing because this baby's got no fire.
And so Joe begins a check of the obvious, the common sense things he checks every time a bike won't start.
Let's see, the ignition switch is on, so is the engine stop switch. Headlight's pretty bright, so the battery should be okay. Well, at least we got some current to crank this baby and run the TPI system. Okay, now let's see. There's fuel in the tank. The fuel valve is on, so fuel should flow through it. Sure enough, it does. It just takes a second to pull the line and check. Man, that one bike with a clogged petcock almost drove me crazy. Well, the fuel seems to be getting to the carbs okay. All the bowl drains have gas, so the lines must be clear. Now then, is fuel getting from the carbs into the cylinders? Well, there's only one way to know. Just crank this sucker for a little bit and see if the plugs get wet. Look here, sure enough, raw gas. There's no problem with fuel flow here. And all the plugs look okay. They're not worn or fouled, no damage. Gaps look okay. This isn't the problem. Compression looks on too. Yeah, just like I thought. Bike this new is usually all right. So let's see if this baby's got enough spark to light the fire. And that's it. No spark, nothing at all. Well, something's screwed up somewhere in the TPI system.
That's right. Joe's done an excellent job. In less than 5 minutes, he's eliminated most of the obvious causes of a no-start problem: switches, battery, fuel, and plugs. But even more important, he's isolated the problem to one specific system. He's ready to focus his attention on the ignition system, knowing that fuel gets all the way from the tank to the cylinders and that the engine can develop good compression. But now, what do you think Joe's next step should be? How should he go about locating the faulty component, connector, or wiring in the TPI system? If you begin thinking in terms of current loops or primary and secondary circuits, you're on the right track. A systematic checkout of current flow through the circuits will lead you directly to the cause of the problem. But to save the time of each one of you inventing the best procedure, we've done it for you. To make your life a little easier, we've prepared a rather comprehensive job aid of TPI troubleshooting procedures. It's being shipped at the same time as this film strip, so it should be at your dealership now. Additional copies are available from American Honda. Each step gives you instructions for a specific test, both words and a picture. Then, based on the results of that test, you're directed to either go on to another step or to stop and fix the problem you've isolated. Let me show you how it works. The job aid begins with a reminder to check all the obvious things that you've just seen Joe check. Switches, battery, fuel, plugs, compression. It's all there. And then, step 1 goes on to ask, any spark? That's the question that Joe asked. And he checked every plug for a spark while cranking the engine. Now, the job aid says that if all plugs spark, the TPI system works. You should check the timing. If that's okay, perform a cylinder leak down test. And if that's okay, then troubleshoot the fuel system. If there's no spark in one plug pair, then you know that the TPI problem is in just that one plug pair circuit. You'll go to step 2. But you can limit your troubleshooting tests to just the affected circuit. If there's no spark at all, well, it is an ignition problem indeed. Go to step 2. There is something wrong somewhere in the ignition system. So let's go back to the shop and give this job aid to Joe. We'll have him perform the tests and show you how the job aid leads you logically and quickly through a troubleshooting procedure. The only thing is, we're going to have poor Joe take you through every step in the job aid. Normally, just a few tests will locate a problem, but we'll show you every test on the job aid. As it stands, we know Joe's 750 has no spark. The next 2 steps on the job aid will now tell you whether the problem's in the primary circuit or the secondary circuit. Step 2 says,
measure cranking voltage to each ignition coil.
And the illustration here shows that you'll connect your voltmeter between the positive terminal on the coil and a good chassis ground. Notice that the black and white wire to the coil is to remain connected for this test. So you'd hook up your voltmeter and measure the voltage at each coil while cranking the engine. This test checks not only the battery's output, but also that all the wires and connectors are okay to each coil. Now, the job aid tells you if you see 0 voltage, it means that there's an open circuit somewhere, and you should trace the power from the main fuse through the ignition switch and through the stop switch. Find and fix the problem. Now, if there's less than 9 volts available to the coil, it means that the battery's low. You should check the specific gravity and recharge the battery if it's needed. Also, it would be a good idea to check the output of the charging system and make sure it's up to specs. Then, repeat step 1. Check for a spark again to see whether the low battery was causing the no spark problem. If the cranking voltage at each coil is more than 9 volts, well, that means the battery's okay. The circuit from the battery to the coil is okay, and you should proceed to the next step. Step 3 instructs you to
measure the cranking voltage drop at each ignition coil.
This test shows you whether or not some voltage is being used by the primary circuit. No voltage drop means the primary isn't working. The illustration shows that you should connect your voltmeter to the 2 primary terminals of the coil. The wires to the coil remain connected during the test. So you'd connect the voltmeter, like you see here, and crank the engine. And of course, you'd repeat the test for each coil. Now, if you find more than 1 volt of fluctuating voltage in your test, it means that you must have a secondary circuit problem. This is the normal reading that shows everything's okay in the primary circuit. So the instructions here tell you to skip a bunch of steps and go directly to step 9. where you would start into tests on the secondary circuit. But if you find 0 voltage drop while cranking, well, that means there's a primary circuit problem. And to test the primary circuit, you should go to step 4. Step 4 asks the question,
Correct pulsar coil resistance?
this test shows you whether each coil measures up to the factory spec for resistance. The instructions show that you'll separate the connector to the pulsar pickup coils. And then, with your trusty ohm meter, you will measure the resistance between each pair of same-colored wires. There's a pair for each coil in the pulsar generator. 1 coil, 1 pair. 2 coils, 2 pairs. 3 coils in the CBX, 3 pairs of wires. Here, you see Joe making the test. He's simply measuring the resistance through each coil in the pulsar generator, between pairs of light-colored wires, yellow to yellow, and blue to blue. Now, the job aid tells you that if there's infinite resistance, there's an open circuit somewhere. You need to either repair the wiring, or if it's okay, replace the pulsar pickup coil. It's faulty. If the resistance through the coil is less than 480 ohms, there's a short circuit somewhere. And again, you should either repair the wiring or replace the pulsar pickup coil. If the resistance is 480 to 580 ohms, that's great. That's the factory spec. And the job aid tells you to go on to step 5. Now, step 5 asks the question,
Is the pulsar coil grounded?
You see, if the pulsar pickup coil becomes grounded, it won't be able to send a pulse to the spark unit. Remember, it's supposed to be an isolated circuit. The drawing shows you how to connect your ohm meter. And what you want to see here is a resistance reading of infinity between chassis ground and 1 wire to each pulsar coil. Here, Joe's performing the test. He's got 1 lead on a good chassis ground. The other lead is touching one of the wire pairs to a pickup coil. It doesn't matter which one, because if the circuit's grounded, it'll show up on either one. And here's the results. If you see less than 480 ohms between any pulsar coil wire and chassis ground, it indicates a short circuit to ground. You need to repair the wiring or replace a faulty pulsar pickup coil. But if you get an infinity reading, it means that the pulsar coil and circuit is properly isolated. That's it for the pulsar loop. The job aid tells you to proceed to the next step. And step 6 asks the question,
Is there power to the spark unit?
This test checks the spark unit power loop to see whether the circuit's okay from the battery to the spark unit and to ground. Notice that the spark unit connector should remain connected. And you'll connect a voltmeter between chassis ground and the black and white wire that feeds power to the spark unit. Here, notice that Joe's touching the positive red probe to the harness side of the spark unit connector, the black and white wire. And of course, both the ignition switch and the engine stop switch must be on to measure voltage. And the results? Well, if you see 0 voltage, it means there's an open or short circuit somewhere between the battery and the spark unit. So using the shop manual wiring diagram, you should trace the circuit and repair the faulty wiring or connector. But if you're looking at approximately 12 volts, the same battery voltage you measured earlier, the spark unit power loop is A-OK, and you should proceed to step 7. Now, this next test is aimed at answering the question,
Is the spark unit operating?
In this test, you'll simulate a pulse and look for a drop in voltage at the spark unit. Notice that you'll be measuring voltage at the same connector as the preceding step. But now, the voltmeter's positive lead is touching the wire from an ignition coil. It creates an alternate path to ground for the primary circuit. Notice, too, that you'll need a wire to connect between chassis ground and the harness side of the connector to the pulsar pickup coil. This wire is used to simulate a pulse to operate the spark unit switch. You'll measure voltage both with and without that ground wire connected. Remember, the spark unit switch is normally open. The pulse closes the switch. Let's look at the test. At the spark unit connector, Joe shifts his positive lead to the wire that comes from one of the ignition coils. With no ground wire connected, and with a pulsar coil connector still uncoupled from our earlier test, the spark unit thinks that it's not receiving a pulse to close its switch. The switch is normally open, and Joe should be able to measure battery voltage in the primary from the coil. Do understand the voltmeter creates an alternate path to ground for the primary circuit, and that's why we're getting a reading here. Then at the pulsar connector, Joe touches his ground wire to the harness wire coated with a white or light yellow tube. This is part of the pulsar loop. Now the spark unit thinks there is a pulse. The switch closes, and the voltage through the voltmeter should drop off to almost nothing because the primary is now properly connected to ground. The circuit through the spark unit has less resistance than the circuit through the voltmeter. Now here's the results. If there's no voltage drop in the primary when the ground wire is connected to the pulsar connector, you can know that there's a spark unit problem. Check the wiring to the unit, and if necessary, replace a faulty spark unit. If, however, the voltage dropped from 12 volts without the ground wire to 0 to 2 volts with the ground wire connected, well, then you can be pretty sure the spark unit's okay, and you can proceed to step 8. And step 8 says,
substitute known good parts.
Admittedly, this is a final effort, but seldom should it be required. Usually, the tests up to here will locate any problem in the primary circuit. However, some problems come and go, especially those caused by heat and vibration. So this is where you'd get into installing known good parts to fix the ignition. Normally, at this point, the ignition would be fixed and Joe would be finished. But let's just suppose that this 750 is a real stinker. Maybe he's fixed a problem in the primary circuit and the ignition still won't make a spark. That means there's also the distinct possibility of another problem in the secondary circuit. 2 failures at the same time aren't very likely, but the job aid can handle it by instructing you to go to step 9. Now usually you'd end up at step 9 because the tests in steps 2 and 3 indicated that the primary circuit is okay, and the problem is in the secondary. You just skip the primary circuit troubleshooting and go directly to the secondary circuit. Now do understand, steps 9 through 12 are the tests needed for a complete checkout of the entire secondary circuit, both the ignition coils and the high-tension cables. And since the secondary circuit on a TPI motorcycle is the same as the secondary with other types of ignition systems, this testing should be a piece of cake for you. Step 9 begins the testing by asking,
is there continuity of the secondary circuit through the coil?
There should be continuity. The drawing shows that you'll disconnect the spark plug cables and use your ohm meter to measure resistance from one spark plug connector to the other. Since there are noise-suppressing resistors in this circuit, you should switch your meter to the 1000 ohm scale to get a reading. Here, Joe's performing the check. The resistance should be around 22,000 ohms. That's normal. But if you get an infinity reading, that's not normal. There's an open circuit somewhere. Check each cable individually. Check the suppressor caps individually. And then check the coil. Replace faulty parts. The job aid shows that if there's any continuity through the secondary circuit, this test is okay, and you should continue to the next step. Step 10 says,
is the secondary circuit through the coil grounded?
Obviously, there should not be any short circuit to ground. And the illustration shows that you will connect your ohm meter between chassis ground and one of the plug cables to look for an unwanted ground. Here, Joe performs the simple check and gets an infinity reading. Now, the job aid points out that if he'd had less than an infinity reading, it means there's a short circuit to ground. You should check the cables, then the coil, and replace the faulty parts. The infinity reading that Joe got indicates that there's no short to ground. This test is okay, and you should proceed to step 11. Step 11 says,
is the coil output acceptable?
The illustration shows that you'll want to measure the length of the spark while cranking the engine. What you want to see is a spark that's at least 6 millimeters long. Joe begins by carefully unscrewing the suppressor cap off one of the plug cables to expose some bare wire. Then, while cranking the engine, he sees how long a spark he can make. Notice the insulated pliers. They keep his body out of the circuit. There are coil testers available that will enable you to measure the spark without pulling the end cap off the wire. Super precision here isn't necessary because a good coil will put out an amazing spark much longer than 6 millimeters. Now, the job aid says that if the spark is less than 6 millimeters, the coil is faulty and should be replaced. But if the coil is over 6 millimeters, well, you go to the last step. And step 12 says,
substitute known good parts.
Rarely will this be needed, but it is the final solution to an intermittent problem. All right, that pretty well wraps it up. In this program, we've shown you how to check the initial timing of a TPI system, both statically, with the engine not running, and dynamically using a strobe light. We've shown you how to check centrifugal advance on several bikes, just following the shop manual instructions. And we've shown you how to check the vacuum advancer on the GL 1100. Perhaps most important, though, we've put into your hands a logical procedure for troubleshooting the TPI system. And we've led you through it step by step. The job aid isn't intended to be a paper brain, just a solid help for those technicians who understand what they're testing. Never will you have to perform all the tests on the job aid. Usually, just a few will nail the problem and help you fix it right the first time. Thanks for watching.